So the last type of oscillator configuration we're going to look at is our Schmitt trigger oscillator. So we're going to look at a couple different types of configurations, one that gives us an astable output and one with a monostable output. So first we're going to consider our astable, and so in our Schmitt trigger configuration we call this an astable multivibrator. And so of course what that means is that we don't have a stable state, so it's just oscillating back and forth between the high and low saturated outputs. And so ultimately what we're going to have then is a square wave. So this is opposed to, if we consider previously when we looked at our Schmitt trigger circuits, we said that they were bistable multivibrators. And that was because they had two stable states. So of course the same two possible states are going to be realized with this circuit we'll see in a little bit. The only difference is with our astable state, neither of them are stable, so it's constantly switching back and forth, whereas our bistable multivibrators with our Schmitt triggers would stay in one state as long as the input was in a certain range. And like I said, we're going to come back in a later video and talk about a monostable configuration. So here's sort of our basic circuit for our Schmitt trigger oscillator, and again just keep in mind this is for our astable. We're going to adjust the circuit a little bit to make it monostable, and we're going to make a couple assumptions here. We're going to assume that we have symmetrical saturated outputs. So basically we're assuming our saturated outputs are symmetrical about 0. So I'm just going to say symmetrical, it's implied it's about 0. So what that means is, let's say our high saturated output V high is equal to some value Vp, and that would mean that our low saturated output V low would be negative Vp. Okay, so a couple things that we're going to do as sort of refreshers before we get into analyzing that circuit. And so some of this could be useful as you're looking at those 555 timer videos. The reason it's showing up in this video and not that one is originally the Schmitt triggers came before our 555 timer. So I apologize if that's a little out of sequence. So the first two things that we want to review is the basic comparator operation. So here we see a comparator which has a reference on the non-inverting input and our input on the inverting terminal. So what we see is as long as that input is lower than the reference value, the output is going to be high. As soon as our input is above that reference value, our output drops to our lower rail, V low. The second piece of review that we want to do is we want to talk about our capacitor voltage for a transient RC circuit. So we can see that's going to be relevant because of course we have this capacitor here, and based on behavior we've seen in our 555, we can imagine that this is going to be charging and discharging based on some time constant. And so of course we'll get to that exact derivation here in a little bit. So in general, our equation for capacitor voltage in a transient RC circuit is shown here below. Vc of t is equal to Vc final plus the quantity of Vc initial minus Vc final times the exponential of e to the negative t minus t switch divided by tau. And so oftentimes this t switch will just be 0 to make things easier, but just for completeness I've put it in this definition here. Keep in mind these Vc final and Vc initial values are values that the capacitor voltage would reach if nothing else happened, if there are no other switching events. In some cases it's not going to reach that final value, but it's just the final value that would be reached if the circuit was left as it is as t goes to infinity. One other thing to mention here is that this tau value in general is going to be equal to Req times Ceq, so equivalent capacitance and equivalent resistance seen by that equivalent capacitance. And so to be consistent with the notes, I've labeled this as equation 1. Okay, so with that sort of review in mind, let's come back to this circuit for our astable Schmitt trigger oscillator. So you'll notice I've added here in blue, I've called this voltage at our non-inverting input terminal V sub plus. And let's make a couple assumptions about the state of this. We know it's astable, so of course it's continuously going to be changing, but let's just sort of make an assumption and jump in and then go from there. So let's initially assume the following. To make things a little easier, let's start out by making this general assumption that R1 is equal to R2 is just equal to some value R. So we're saying that those two are equal. And that's going to be handy because what we can see is we have a voltage divider here. So if they're equal, we can just say it's going to be half of the value. We don't have to worry about calculating ratios there. And here is where sort of our assumption about the state comes in. Let's assume that our output voltage is equal to the low saturated state, which in our previous assumption we said was equal to negative V sub P. And again, keep in mind, we know this will change because this is an astable oscillator. So it's not going to stay here. It's just going to be flipping back and forth between positive VP and negative VP. Okay, so if this output then is negative VP, so that's the voltage here. So now we can consider this voltage divider circuit that I highlighted a second ago in order to figure out this V plus value. So let's go ahead and do that. So we can say our V plus, the voltage at our non-inverting input terminal, is just equal to 1/2 times the V out, which is negative VP. And so again, that comes from voltage division. So now we notice that this V plus is serving like our V ref when we looked at that ideal comparator operation, and our V in is this Vx value here. So what we can see is when this Vx drops below V plus, the output is going to switch high. So let's come here and we can say when our Vx, which is acting like our V in for that simple comparator we considered, drops below the V plus, then the output is going to switch high. So once our output switches high, we can then change our conditions for our output, of course. So we have V out is equal to V high, which we said in sort of the very first time we wrote that circuit is equal to VP. So now coming back to the same voltage divider circuit over here, what we can see is now our V plus value has changed. So now our V plus is equal to 1/2 times positive VP. And so again, that's from voltage division. And so what's happening now is our capacitor, CX, is going to be charging up towards VP. So our CX begins charging up towards VP. So let's take a look at the circuit and see why that is. So if we come here and we say, get rid of some of these, we say we have some positive voltage here, and that's being applied through this network here. We see if that output is more positive than our Vx, which we know it will be, then because our Vx was just decaying below negative 1/2 VP, then we're going to be charging this capacitor. And so as we can see, that's charging through Rx, so our time constant is going to have our Rx as well as our Cx, of course. So let's write our equation for our capacitor voltage during that charging cycle. So we can say our equation is Vx, which is going to be a function of t, is equal to final value, which is Vp. Again, this is considering nothing else is going to happen, it's just going to keep increasing. We know that's not true, but if it were, it would eventually reach Vp in steady state. Initial value is negative Vp over 2 minus final value of Vp times exponential of negative t divided by tau. So we've just arbitrarily said that our switching time was 0. Tau is equal to Rx Cx, as we saw a second ago looking at the circuit. So let's simplify this a little bit, and we have Vx of t is equal to Vp minus 1.5 times Vp times e to the minus t over tau. And to be consistent with my notes, it looks like I have this labeled as tau sub x, but I'm going to leave that as tau for now. And so let's call this equation 2. So this is going to be an equation for when our capacitor is charging up. So during this time, our capacitor is charging up, but keep in mind, now we have this value of V plus equals 1/2 Vp. So going back to our basic comparator operation, that's serving as our reference. So as soon as our voltage gets above that, our output state is going to switch again. So to be specific, we can say when our Vx increases above that V plus, then our output is going to be switching low. And so if our output switches low, of course we're going to have V out will go back to being VL, which is equal to negative Vp, as we've said before. Our V plus is going to go back to being negative 1/2, or let's say 1/2 times negative Vp from voltage division. And our Cx is now going to be discharging. So our Cx is discharging, and it's going to be discharging towards negative Vp. We can also think of that as charging up towards a negative voltage. In terms of saying charging, discharging, it's maybe easier to just write it in terms of the equation. You'll notice I've got some stuff peeking through there from the next page, so just ignore that for the time being. But we can say our Vx of t is going to be equal to our final value, so it would finally go to a voltage of negative Vp if nothing else happened, plus the quantity of the initial value, which was Vp over 2, minus the initial value of negative Vp, times exponential of negative, now I'm going to have t minus t1 divided by tau, and so we're going to have that same time constant tau equals Rx times Cx. Okay, so cleaning that up a little bit, I can say Vx of t is equal to negative Vp plus 1.5 Vp e to the minus t minus t1 divided by tau. And so t1 is just the time when the output switches low. So let me write that explicitly here. So we've got t1 is when output switches low. Okay, so, and to be consistent with the notes, let's call this equation 3. And so before we come back to these equations, well, actually, one more thing we can say is, of course, here, based on equation 3, we can see our Vx is going to be dropping. And so as our Vx is dropping, eventually it's going to drop below this reference level of V plus, in which case our output is switching high, and we're just repeating through this process. So charging, discharging, charging, discharging. And so the end result in terms of the output is our output is switching between negative Vp and positive Vp. So we just have a square wave as we predicted. Okay, so let's look at sort of our plot qualitatively, and then we're going to calculate some values for our period and our frequency. So here I have sort of a basic plot laid out for us. We see we're plotting our output voltage over time. I've got our high and low outputs. So up here we have our high of Vp, our low output of negative Vp, and then I've got our important voltages of Vp over 2 labeled in both of those. Both of those are labeled as well. So what we're saying is that initially, if we're charging up, so let's say we came in here when we were charging, so coming all the way back here, we said initially, well, our plot's going to be a little different to match with the notes, but let's say initially we had our voltage at our V plus was down here. So I'm going to plot in red, this is going to be our V sub x, and I'm going to plot the output in blue in a little bit. So what our Vx is doing, if we're coming in on this charging cycle, it's going to be charging up towards VP. And so what that looks like with that exponential term in there is maybe something like this. So we have something like that. But remember, once we hit that VP over 2 mark, we're going to be switching our output states and our capacitor is going to begin discharging, or another way to think about it is charging towards negative VP. So what we actually have, and so let me try to line this up with my times, is we have something that looks like this. So this would have gone towards VP. So we were charging towards VP, but at that point our output state changed and we begin charging towards negative VP. So if we're charging towards negative VP, this is now our starting point and we have something that looks like that, and it'd be going towards negative VP. That's a pretty terrible curve, but you kind of get the idea. It should have some 1 minus an exponential. But again, as we get to negative VP over 2, we are changing our output state. So we end up with something that looks like this. And so that would have continued on towards negative VP. So then the same thing just repeats itself. So we have this would be going towards positive VP, but as it reaches VP over 2, it gets cut off. So that would have been going towards VP. And then same thing here, this would be going down this way, but it gets cut off at our negative VP over 2. So we get something that looks like that. Okay, so now let's draw our output sort of superimposed on top of that. So during this charging state, remember we said that our output was high. So let's come up here where we said, in this case, we say it is charging. So here we say we're charging. And in this case, we see that we had our output is high. And then similarly, if we were discharging or charging towards negative VP, we had a low output. So that's pretty easy to superimpose on top of this. So if we're charging towards VP, we have our high output state up here. At this point where it crosses over VP over 2, we switch to our low state. So let's see if that'll straighten that out for me a little bit. And we stay at our low state until that reaches the threshold of negative VP over 2, at which point we transition back up to our V high. And we stay at our V high until we hit that transition of VP over 2. And then we go to our low state. So you can see everywhere that we're charging towards VP, we're high. Everywhere that we're charging towards negative VP, we're low. So this blue curve would then be our output voltage. Okay, so that's sort of the general qualitative plot. So now let's see if we can't figure out some equations for some of these times, and then ultimately from that get our frequency. So let's start by saying we want to find this time t1, the time on. Then we'll find a ratio or the difference between our time t2 and t1. Ultimately we'll find t2, and then 1 over t2 is going to be our frequency. Okay, so in order to find t1, we're going to come back to our equation 2. So in our equation 2, what we're going to do is we're going to use t equals t1, and we know at that point that our voltage Vx is equal to Vp over 2. So we can see that from the graph right here, and we can also see that from our conditions up here. When we're charging up, we know that once we hit this Vp over 2 point, that's where we switch and we'll be discharging. But that occurs when we have Vp over 2. Okay, so if we plug that into our equation 2, what we have is we have our voltage is Vp over 2, and our equation says that's equal to, in general, Vp minus 1.5. It looks like I've left out a Vp in the notes, but that should have a Vp as well. Yeah, so I've just left that out on this page. Times e to the minus t1 over tau. And so what that reduces to then, our VPs are going to cancel out, and we'll have 1/3 equals e to the minus t1 over tau. And ultimately then we can solve that for t1, which is equal to negative tau log of 1/3, which is equal to negative Rx Cx natural log of 1/3. So we can say T1 is approximately 1.1 times Rx Cx. Okay, so that's our value for T1. So now let's do similar analysis. And so I'm not going to show all the details this time, but if we do similar analysis to figure out the distance between T1 and T2, so we can say T equals T2 and Vx equals negative Vp over 2. If we put that into our equation 3, what we get is an expression for T2 minus T1, and we find that that is approximately 1.1 times Rx Cx. Okay, so what we can do then is we can say, well, the period is just equal to T2. And so we can kind of play around with these two equations we had before. We can say, well, T2 is just going to be this equation plus this one. So that's going to be 2.2 Rx Cx. So our period is approximately, so let me come back and change this to approximately. If you want to keep exact terms, you can keep those log terms in there. So Rx Cx. And then, of course, our frequency, which is just 1 over the period, is 1 over 2.2 Rx Cx. So that there. So a couple things to note about the general behavior of our Schmitt trigger oscillator based on these equations. One thing we note is that if we use a potentiometer for our Rx value, we can easily change the frequency of our oscillator. So potentiometer for Rx yields easily adjusted frequency. And so let's go back up to the circuit real quick just so we can remind ourselves where that Rx is. So we see that's this value here that is sort of serving as the feedback from our output to our inverting input. We could also use a variable capacitor. It's just often more, variable resistors are more readily available, but we could also have a variable capacitance for Cx, which would also allow us to adjust our frequency. So a couple questions to ask yourself. So maybe pause the video while I write this and then think about it. But what effect do we have from using different R1 and R2? So what effect does different R1 and R2 values have? So again, maybe pause the video, maybe rewind, go back, look at some of the circuits in the tables, and think about how changing R1 and R2 would affect this response. So what we can see is ultimately changing values of our R1 and R2 right here is going to change this voltage division equation. So we had our voltage division here where we found our V plus with a low output, and we have our voltage division here where we find our V plus using our high output. And so with the two values being equal, we have 1/2 Vp. Well, if we change one or both of those, or ultimately if we change the ratio between those, this 1/2 Vp value is going to change. And so what that means is that we're going to have this sort of threshold value here either moving up or down. So either they're both going to be moving closer to the high and low voltage respectively, or we could also see them moving closer towards 0. And so in both cases, what that's going to be doing is that's going to be adjusting the frequency. So for a fixed Rx and Cx, this red curve is going to be increasing or decreasing at the same rate, depending on whether we're charging or discharging. So it's going to hit that threshold sooner for this orange case, which means a higher frequency, or it's going to hit the threshold later for this green case, which means a lower frequency. So ultimately, what does this do? Well, this allows us another way to adjust our frequency. So one other question for you to think about is, can we adjust the duty cycle? So can duty cycle be adjusted? And so again, it might be good to pause the video, go back to the circuit, go back to the plot, think about this a little bit. So we've already talked about changing all of these variables. We've talked about changing R1, R2, Rx. We talked about you can change Cx. It's easier to change the Rx typically though. So what else do we have left to adjust? Well, the answer is we can change this assumption we made at the start about having symmetrical saturated outputs. So if we have asymmetrical outputs, then we're going to have, we can adjust our duty cycle. And so we can do that if we're talking about an op-amp in the lab. We have those offset pins where we can adjust our low and high saturated values. And so to see that more clearly, you can go back to these equations that we had written here to see how that's going to change our charge and discharge times and ultimately change the duty cycle. So let's just come down here and write yes. And we can do that by using asymmetrical outputs. So in our next video, we're going to come back and we're going to make some slight adjustments to this circuit, and we're going to see how we can create a monostable Schmitt trigger oscillator.